Yeah? Okay, just one sec. Okay. Yes. All right. Thanks a lot. Okay. So let's see. So we're starting chapter 3 now, which is going to be an application of this mirror descent framework for metrical task systems on trees. So we're going to see our first algorithm derived from the mirror descent framework. And as a warm-up, we will do weighted stars. Okay. So here is a theorem that we're going to prove. So theorem. On X, which is the following metric space. So I will draw it as a tree, but really it's just a kind of uniform space, but with weights. So these are the leaves, like this. So this is X. These are the points in X. And the metric is just given by weights on the edges. So you have W1, W2, etc. up to Wn. Okay, 1, 2, up to n. So this is my metric space. So if I'm in location 1 and I want to go to location 2, I pay W1 plus W2, and so on and so forth. Okay, so this is the metric space. So on X like this, mirror descent with potential that I will explain gives O of log n competitive strategy for metrical task system, for MTS. Right, and MTS, remember, this is what we have been focusing on. Every time step, you get the cost function. You know, you decide whether you want to stay in your state and pay the cost there or move to another state. Okay, so this is what we were explaining before. And of course, it's a randomized strategy. Okay, so just to clarify a little bit, this question was open for almost 20 years. Okay, and the breakthrough paper that solved it was this Bensal, Burbinder, and Naor that I already cited maybe in the second lecture. And they used these primal dual schemas, and you know this was really a breakthrough. We'll see that for us in our framework, it's going to be 2 lines once you set things up correctly. And in particular, the fact that it's so simple in this mirror descent framework will allow us to go beyond just a single star. Okay, so just looking forward. So looking forward, here is the ultimate goal for this lecture, and then again tomorrow we will move to K-server. So looking forward, we're going to prove a theorem, and this one is new. So this one is BCLL 18. So the theorem that we'll prove is that on X, which is now a tree, okay, so you have level 1, but then you have a level 2, etc., you know, like this. So you have multiple levels, and you have weights. So say, you know, if this is node U, you have a weight WU. Okay, so this is a weighted tree. So on trees like that, and let's say the depth is D, depth capital D, we'll show that on weighted trees like this, a slightly non-trivial extension of this proof will give us a D log n strategy. Okay, so on X like this, mirror descent gives a O of D log n competitive strategy. Okay, so that's what we're gonna do now. to put this in perspective, this gives you something now for arbitrary metric spaces. So again, there are a couple of things that I'm going to ignore in those 5 lectures. One of them is approximating general metric by tree metric. So I'm not doing that, but it turns out that you can approximate general tree metric by general metrics by tree metrics, which have depths log n, and you pay a factor log n. So what this will mean is that D in general will be log n, and there is another log n that comes from the approximation of general metric by tree metric. So this theorem by itself gives you a log cube n for general metrics, for arbitrary metrics. And I mentioned at the very beginning that we know a log squared n. So we know a log squared n because it is possible to improve this theorem, where instead of D times log n, you can get D plus log n. But for this, you need to make more assumptions about the weights. So this is what's called the HST case, hierarchically separated trees. So in HSTs, those weights are exponentially decreasing along any root leaf path. Okay, so maybe it's 1 here, then 1/2, then 1/4, etc. And it turns out that general metrics, you can exactly approximate them by HSTs. Okay, so for HSTs, instead of multiplying like this, we know how to get plus. So this gives you log squared instead of log cube, but it becomes pretty technical, and in fact, we didn't know how to do it using a pure mirror descent approach, but there is a recent paper by Christian Koester and James Lee that shows that exactly what I'm going to show you today, you can use it on HST to get D plus log n, but it becomes much more complicated. Okay?
That setup, you pay a weight U for going down the tree from node U instead of up the tree, right?
Yeah, any way you like. If you know, as long as you traverse this edge, you pay WU, whether you traverse it upwards or downwards.
And from the
Okay? As long as you just travel in this tree, and if you travel along that edge has length WU.
I think the question is whether the other link connected to U is also double.
Oh, the one up there.
No, they're right.
Oh, I see. Okay, very good. Sorry. Yeah, okay, thanks for the question. No, I want it above. This is WU. Sorry, thanks for the question. Yes. Yeah, the picture was wrong. Okay, good. So let's start. Hopefully we can prove both theorems. Yeah.
Sorry, when you say that you can approximate any metric space
Yeah.
with that kind of metric,
Yeah.
you mean finite metric space?
Yes. I mean, the approximation error that you make is log n. So, you know, if n is infinite, you don't have anything. Yeah. I mean, this is a whole field, metric embeddings and metric approximation. So yeah. Okay, so let's do this one. So we know from the previous lectures that if you run mirror descent with any mirror map, you get an inequality, which is 1 Lipschitz. You will get an inequality, you know, like this. As the service cost is bounded by the service cost of up plus the movement cost of up. So again, the only thing which we have to do is to worry about the movement cost. Okay. So maybe I should spell out now what is the norm that we're going to look at and what is exactly the framework that we apply. So we apply the mirror descent framework with the convex body K, which is simply the simplex. Okay, we don't do anything fancy. We just literally move probability distribution. And the norm that we use, the norm H, is just a weighted L1 norm. It's the sum for I equals 1 to n of Wi, absolute value of Hi. And I claim that this is, and it should be easy to see, that this is the W1 norm. This is the Wasserstein norm for this metric space. Why is that? You know, imagine that I have my H. Okay, so H is a vector, and H is saying, you know, here you add maybe H1, you know, plus H1. Here you have maybe a minus, you know, minus H2, etc. So, you know, the vector H is telling you if you have a zero mass everywhere, now I want to bring H1 mass here. I want to augment the mass by H1. I want to reduce the mass by H2, etc. So to understand what the Wasserstein distance is, I need to give you a transport plan. How do I transport mass to satisfy all of this? What am I going to do? So let's look at all the negative locations. Let's say these three are negative, and these 4 locations are positive. So first of all, I know that the sum is 0. Okay, the sum of the HI is 0. If this is really, I'm moving, I'm conserving mass. So all of those negative things, what I can do is that I can send this mass, I can borrow mass from all of those locations and send them to the root. How much do I pay? Well, for this one I pay H2 times W2. For this one I pay H3 times W3. So I send everybody all the negative mass, I borrow mass from those locations, I send it to the root. I store it at the root. I store it at the root. It's virtual, right? I don't really do that. And then for those guys, I send it back. So this guy, you know, it has to grow by H1. So I send H1 mass through this edge. So I get H1 times W1, and etc. So this norm is exactly the norm that measures movement. Okay. Good. So now we have to work. Now we have to come up with a mirror map. Okay, so how are we going to come up with a mirror map? So phi is a general, you know, multivariate function. It can be very, very complicated. But this seems to be a simple enough structure that I think it's reasonable to look for a separable mirror map first. So let's do that. So let's try phi of x, which is of the form, the sum for I equals 1 to n of some phi I of xi. Okay, just look at a separable function. These functions are much simpler than general functions. In particular, the Hessian, you remember the mirror descent dynamic depends on the Hessian, and I need to invert the Hessian. The Hessian at x is nothing but a diagonal matrix where the diagonal element are the second derivative of those phi I. Okay, so when I want to invert this matrix, I just get 1 over phi I double prime. Okay, so the formula, remember the formula of mirror descent is the derivative of xt at xt is minus the Hessian of phi at x inverse applied to c plus lambda, where lambda is in the normal cone of k at x. So this is the general formula. Now with k being the simplex, remember the simplex is just, again, it's all the x such that the xi's are non-negative and the sum of the xi is 1. So when I apply this formula with k being the simplex, we did it before, we're going to have 1 Lagrangian term for each of those non-negative constraints, and we're going to have 1 Lagrangian term for the equality constraint. So this will be lambda, I'm going to write it down. And the inverse Hessian, we know what it is. It's 1 over phi I double prime. So what we find is lambda, as I explained before, it's minus the sum for I equals 1 to n of some psi I ei. And then you have some other term, which I'm going to write as, let's write it as plus mu. Plus mu times the whole 1. So this is lambda, that's what we did before. You know, 1 Lagrangian for each of those, and 1 Lagrangian for this. So the psi I are non-negative, and strictly positive means that xi is actually 0. Okay, you're only non-zero if the constraint is tight, and mu is just a real number. Okay, because it's an equality constraint. So this is lambda. Now what about this formula? This formula is now just telling us that the time derivative of say the ith location, this is equal to what? So the Hessian inverse is minus 1 over phi I double prime of xi of t. And then what do you get? You get ci, then plus lambda, so ci minus mu, and maybe let me put a minus here. That would be nicer. So plus mu, and then plus mu, no, minus mu, very good, plus minus xi. Okay, so this is the formula that you get. Okay, so let's try to understand a little bit this formula. So let's ignore this term for a moment. First of all, phi I is convex, so this is positive. Okay. Now you see, if there is a large cost, then I'm going to decrease more rapidly at location I. Now, of course, if I get to 0, you know, I want to decrease so much because I have so much cost that I reach 0, I cannot go below 0. So this term is just ensuring that I never go below 0. If you want, the right way to think about it is that Ci minus Xi, we're going to call it the reduced cost. So at some point, I obtain so much cost at location I that I'm at 0. I have 0 mass. I just don't want to be there. So then, you know, the cost might continue to raise as much as it can, but the algorithm is not going to see it because it starts to have a Lagrangian term which kills it. Okay, so we're going to call this the reduced cost. It's going to be slightly important. Yeah?
Let me check. So Ci is the cost function or the gradient?
It's the same thing because we are in the setting, by the way, it's Ci of t. Ci of t, and these are Xi of t and mu of t. Sorry, there are t's everywhere. Ci, it's both the cost and the gradient because in this setting, when we play a randomized algorithm, the cost function on the state space becomes a linear function on the probability distribution. And the gradient of a linear function is the function itself. Okay? So it is the cost. It is the cost at this location. And now, what is mu t doing? So you see, all this is doing is that it's decreasing stuff. So the only possibility is that mu t is non-negative. Okay, so important. From this formula, we see that mu t is actually non-negative. This is not a consequence of the Lagrangian general formulation. It's a consequence of this formula. Mu t cannot be strictly negative because if it is strictly negative, then everything decreases. And you know, if everything decreases, then so this is because the sum of the derivative of the xi of t must be 0. Right? In total, things are not changing. I have conservation of mass because the sum of the xi is equal to 1. So this Lagrangian term mu t, we know that it's non-negative. Okay, so again, what's happening in terms of a picture? So we have our star like this, and we have those costs, C1 up to Cn. So those costs, they induce some decrease. Okay. Let's imagine, simplify for the moment, and think that there is a cost only at a single location. This cost, so think, maybe let's think it like this. Think C is just E1. Okay, just example. Think that the cost is just a unit cost at location 1. So this unit cost, it induces some decrease over there. Okay, this is this part. And think for the moment that the Xi are 0. Okay, nothing is at 0. So the algorithm wants to decrease at location 1. But this decrease at location 1, it needs to be dispersed to the other location. And the way the decrease at location 1 is dispersed to the other location is through this mu t. This mu t is doing the redistribution of mass. Okay, so this decrease is now being sent to all the other locations. And all the other locations are going up. So they are going up, thanks to mu t. And this goes down because of the cost. So that's what the algorithm does. Okay, there is a cost at some location, I decrease, and I need to send the mass somewhere else, and it's going to be sent according to, and now that's where the mirror map is very important, according to the second derivative of the phi I. Okay? And this type of picture is going to be more complicated on the tree. On the tree, you know, mass is going to flow everywhere, and we'll have to understand what's happening. But now let's conclude the proof. Okay, so let's conclude the proof. So what do we care about? We care about the norm of the time derivative of xt. But we're gonna notice that we have some choice. We can also just look at the norm of the time derivative of the negative part of this, or if we want, of the positive part. This is going to be a very nice trick. So up to a factor 2, if I want to control this, it's enough to control that or that. Right? Because everything that comes in eventually comes out, or it stays there forever. Okay, so this is what comes in, this is what comes out, this is the total balance. But again, either the mass enters and then never leaves, and then it's just some additive constant, or if it goes, if it exits again at some point, it's going to be measured. Okay, so again, up to a factor 2, I can choose to control this, that, or that. But remember, our key is we already know the service cost is good. We only care about the movement cost. And you see the movement. So the movement which is induced by the cost, it's very special. We know exactly what it is. It's this thing. It's Ci over phi I double prime. So let's just look at the negative movement. Okay, so for now, for this proof, we're going to only consider this one. Okay, and up to a factor 2, it controls that one. All right? So what is this? So the derivative of xit. So the negative part. So let's lower bound this. So we know that this is bigger than minus Ci of t over phi I double prime of xi of t. Okay, so this is always true because all the other terms are non-negative, right? There is a minus, 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 minus. This is non-negative, this is non-negative. Okay, so we know this is true. So the norm of the derivative of xt, the negative movement, we know that it's upper bounded by the sum for I equals 1 to n of Ci of t over phi I double prime of xi of t. And what is the service cost? The service cost, the instantaneous service cost, is just the sum for I equals 1 to n of Ci of t times xi of t. So this directly suggests, let's take 1 over phi I double prime to be equal to xi. Okay, so natural to take phi I such that, there is a wi I'm missing. Right, it's a weighted L1 norm. So it's natural to take phi I such that wi over phi I double prime of, say, a variable s, or let's say of xi, is equal to xi. Okay, if I do that, then this quantity just becomes equal to the sum for I equals 1 to n of Ci of t, xi of t. Okay, so if I take a mirror map, which is, again, this form, the sum of phi I of xi, such that each of the phi I of xi verifies this differential equation, then I get that my negative movement is exactly upper bounded by my service cost. And my service cost itself is upper bounded by opt, and I would have a 1 competitive algorithm, or a 2 competitive algorithm. So something is too good to be true right now, but this is what we want. So yeah.
Why do you say that the derivative of the service cost?
Yeah, service cost is just the integrated thing. Yes. Just a question of definition. Okay. So what is this differential equation? Well, you can just solve it. It's so this equation is implied by phi I of xi, which is wi xi log xi. Okay? Or in other words, phi of x is the sum for I equals 1 to n of wi xi log xi. Okay, and this you really you must love it that we get this formula. So this is just a weighted entropy. Okay, it's very, very natural, and it falls out of everything we've done. Okay, so does someone see what's the problem? Because it's too good right now. This gives us a too competitive algorithm. So there must be a problem. So remember this inequality was true if phi is 1 Lipschitz. The entropy is not Lipschitz on the simplex. The gradient is log xi. So the gradient goes to infinity when the xi goes to 0. Okay. So phi is not Lipschitz. And this is actually very fundamental. This is not a minor thing that's happening. This is kind of the crux of everything. This is where the competitive ratio is going to appear. It's because we cannot take this because it's not Lipschitz. Okay. But fortunately, people in online learning community have also solved that problem. And people in online algorithms also have solved it, but using some magic, and I think in online learning it's very clean what's happening. So I will explain that. Is there a question? No? Okay, so again, the only thing we have to do right now is to somehow apply some surgery and make sure that phi is Lipschitz. And the Lipschitz constant is going to drive the competitive ratio. What do I want to erase? So I'm going to keep the dynamics. Of course, I didn't say it, but the dual norm is just an L infinity norm, right? I mean, the dual of the L1 norm is just L infinity. Okay, let me use another color. So fix to Lipschitz issue. Can you see with the color red? Is that okay? Yeah. Okay, so the fix to the Lipschitz issue is to add a little bit of mass everywhere, to act as if things never got to 0, but they were lower bounded by some delta, some little delta. So instead of this formula, I'm going to take the sum of wi xi plus delta log xi plus delta. So let's take phi of x, which is the sum of wi xi plus delta log xi plus delta. Okay, so now this is going to be Lipschitz, right? The gradient of this phi of x is just wi over xi plus delta. Okay, plus some constant, which doesn't matter. Let's forget about the constant. Okay, I can just add a linear function such that there is no constant for I equals 1 to n. So the dual norm here, the dual norm of H, if the primal norm is this weighted L1 norm, the dual norm is a weighted L infinity norm. So this is a max over I of the absolute value of Hi over Wi. So you see that the dual norm of the gradient, this is equal to the max of 1 over xi plus delta. And what did I do? There is a log missing. Sorry, guys. There is a log missing. The gradient is wi log xi plus delta. Okay, so the dual norm is the max of log xi plus delta in absolute value. So this is smaller than log 1 over delta. Right? When xi is 0, this is log 1 over delta. Okay, so we get that this function is log 1 over delta Lipschitz. Okay, and just to have this nice formula where it's 1 Lipschitz, let me add a 1 over eta here. 1 over eta. Here I get 1 over eta. I get log 1 over delta over eta. Okay? So with eta equals log 1 over delta, phi is 1 Lipschitz in the sense that we were defining before. Okay, so this formula now applies. Now, of course, this slightly changes the dynamics. And it has to, because it's not just a technical issue, it's really the algorithm doesn't work. If you don't add this plus delta, the algorithm is basically moving too slowly. Okay? And this is a very well-known problem. That's why it was introduced in online learning, because this type of strategy, this multiplicative weight strategy, it's known to have a regret bound. So it's known that it can compete with a static best expert, but it couldn't compete with a moving expert. And the reason why it couldn't compete with a moving expert is that it was moving too slowly. So people added this delta so that it's kind of a prior which is always there. So in learning theory, we think about it as mixing with a prior distribution at every time. You see, this is your distribution right now, and you're mixing it with some extra prior distribution. Okay, so that's the way people were thinking about it. And really, it makes it that the algorithm is moving faster. But that's not good. We want the algorithm to not move too much. But of course, it makes sense. I mean, right now, I could take delta as big as I want, it seems. And I'm not paying anywhere. So where is it that you cannot take delta too big? It's going to appear now that if delta is too big, then the algorithm moves too much. Okay, so now I just need to redo this bound. I just need to look again, how does it change the dynamics, and what is the extra movement that this induces? Okay, so that's what we're going to do now. So let's see. The only thing I have to do is here. This was the only place. So now, instead of having this differential equation, we have a plus delta here. Okay? So what this means is that here, instead of ci xi t, we have ci xi plus delta. Okay, so this is all that's happening. So let me write it in inner product form. So this is ct dot xt plus, let's write it like this, delta as a vector delta which has coordinate all equal to delta times ct. So this is my movement cost. My instantaneous movement cost is now the service cost plus a new term. Okay, so maybe I move back to black. So I want to try to conclude. So, okay. So what is this delta times ct? So this is some extra movement that is being introduced. Well, on the face of it, this looks terrible, because what happens if one of the costs is very, very large? If one of the costs is very, very large, then this is moving like crazy. But we're going to be saved by this comment, if you still have it in mind that I was saying, this reduced cost. The algorithm doesn't see huge costs. If a cost becomes so big that it brings the value of the location to 0, then in fact it doesn't see the cost anymore. It sees ci minus xi. So there is never a big cost. There is no big cost. Okay. So in fact, let me make this modification. Really, in the negative movement, I could have written ci minus xi of t. Okay. But psi t inner product with xt is 0, so the only thing that's changing is that this is minus psi of t. Okay? And yeah, this is minus psi of t. Psi of t. Okay, so this was an important point, and I realize it might be a bit confusing, so ask me a question if there is a question. So again, now it's ct minus psi of t. Okay, so at least we know it's not done yet. We don't know yet that everything is fine, but at least we're not in such a terrible situation. Okay, and what's going to happen now, I'm going to tell you in a minute, but what's going to happen intuitively is that what's going to happen is that those costs, they are all of the same order. Basically, if one cost is much bigger than the other, then you just bring the location to 0. So what we're going to show is that all of those costs, they are of the same order for every location. So basically this, we're going to show, so to be shown, is that this is going to be of order n times delta times CIT for any good I. For any location I which is not at 0. And that this is in fact going to be n times delta times ct.xt. So you see the price, the additive price that you pay is n delta. Okay, so if that is true, if this little thing is true, then the movement cost, instead of being just the service cost, is going to be 1 plus delta n the service cost. Okay, so let me say that again. So if true, then we get this bound. Then we get that the norm of the negative part of the movement is upper bounded by 1 plus delta n times the service cost, ct.xt. So now we will see now here the price that you pay if you put a delta too big. If you put a delta, say some constant, you move like crazy. You move like n times your service cost. So if you put a constant, yeah, you constant Lipschitz, but your movement becomes, n times your service cost. So here's the bound that we get, right? What is mt? We just showed that for this algorithm, mt is upper bounded by 1 plus delta n times st for the negative movement. Okay, so you just should take delta. You should just take delta to be 1 over n. And of course, there is an eta that's missing a little bit everywhere. I have normalized by 1 over eta. So really the movement, there is a eta here. Okay, so this is the true, this is what we have proven. We know that the service cost is bounded by opt, and we know that the negative movement is bounded by eta, which comes from this 1 over eta, times 1 plus delta n. The 1 plus delta n comes from those two terms, times the service cost. So now take delta to be 1 over n, eta to be log 1 over delta, and there you have it, your log n competitive. Okay, so the only thing that's missing is this little fuzzy part. Okay, now is a really good time for a question. Okay, let me take it.
So how do you set eta?
You set eta, so just to simplify things, this bound, eta is log n. Eta is log n. Yeah.
Where about the complete movement, you just have to lose a 2?
Yeah, you lose a factor of 2, so this is the negative movement, and mt is bounded by twice mt minus plus some constant. I guess I lied when I said that it was going to be 1.9. Yeah, sorry. Okay.
So these reduced costs are actually just the cost that your exam contained
Yeah, these reduced costs are exactly the costs that mirror descent naturally maintains, exactly. So this is the perfect way to put it. So really, these costs could be huge, but again, if they are too big, you get to zero, and then you just don't see them, the adversary could put infinity costs there. I'm already at zero. I'm not going to reduce further. So this minus xi is just exactly subtracting this too much. Okay, so now I'm going to give you a little lemma to prove this, which is kind of nice, and I will give the proof as an exercise. It's an equality, so it's easy, but okay. Okay, so the lemma is the following. Let me make sure I get it right. Yeah. So lemma this delta. Okay, let me make it more general, the lemma, so that it will be useful for us. So assume K is of the form all the x such that the xi are non-negative, and Ax is smaller than B for some matrix A. And let delta in K such that A delta is in fact equal to B. Okay, so for us right now, in what we have been talking about, K was just a simplex. So this was just two inequalities, one that the sum is smaller than 1, and one is that the minus the sum is bigger than minus 1, or smaller than minus 1, sorry. So you just have those two inequalities. So this fact, in our case, just means that the sum of the delta is equal to 1, which exactly means delta is 1 over n. Okay, so if you have that, then the reduced cost, so delta times the reduced cost, Ct minus xi t. So xi t just comes from those non-negative constraints. This is smaller, this is equal to actually what the algorithm is paying plus a potential drop. So the time derivative of the Bregman divergence between delta and xt. Okay, so this is exactly saying basically what we were saying here, is that delta times the reduced cost is the service cost, provided that n delta is equal to 1, which here we write it as A delta is equal to B. Okay, so this is just a more general lemma. It's an equality, so the proof is exercise. And this concludes the proof. Right? Now that we have this, we know that delta times the reduced cost, which is this extra movement that was introduced by adding this plus delta in the entropy. So this extra movement is in fact just equal to the service cost plus some terms that integrates to a constant. Okay? And the condition was that A delta is equal to B, which in the case of the simplex just means that the vector delta, all of its coordinates, they sum to 1. Okay, so yeah.
So what's the reason again of the other term, the right term?
Yes. Very good. Yeah. So this is the time derivative. So when you integrate, so all you care about those things, you never care about something instantaneous. All you care about is when it's integrated over time. But when you integrate a derivative, then you just find the value at the end minus the value at the beginning, which is some constant. So this is like st. So yeah, I mean, if you just integrate, you will get this added movement is the service cost plus some constants. So again, yeah, what you will find, okay, thanks for, you will find that this is true plus a constant. Yeah, this was missing, yeah. Okay, I give you a few more seconds to think about what I said, and then we move to the more difficult case of the tree. No, because I put a minus here. But if it was a true empty, then yes, it would be 2 times this plus a constant. Yeah.
And this constant doesn't depend on any parameter of the problem. I also consider that
It depends on the diameter of the metric space.
Okay.
Yeah, it will depend on the diameter of the metric space. Yeah. Okay. Okay, so let's move to the tree case. Okay, so again, now our metric space is this guy. So the first thing that I want to say is what is the norm for the movement. So given so now we're going to have V are the vertices of the tree, all vertices of the tree, and L are the leaves, and this is our metric space. This is X. Okay. So X are just the leaves. Okay, and the internal nodes are just there to monitor the movement. That's all it is. So if you have H in R to the L, okay, such that the sum of the HL is equal to 0. Okay, so H is some movement that you want to make on the leaves. How much movement will you make? So I claim that the following formula is true. So define H hat of U, where U is a vertex in V. So define for U in V, H hat of U, which is just the sum over all the leaf such that U is an ancestor. Of HL. Okay, so the picture is like that. So if this is vertex U, H hat of U is the total change that I must make in that subtree. Okay? So for instance, if H hat of U was 0, then it means that all the change that I have to make in that subtree, I can make it within that subtree. I never have to leave that subtree. If H hat of U is 0.1, it means I need to it means the total mass of the tree, of that subtree, is going up by 0.1. So I need to bring in 0.1 mass. So certainly I need to pay 0.1 times WU. Right? And in fact, this again gives me a plan. I can just do it as I did it before. So the formula that I'm going to get is that the W1 norm of H is equal to the sum over all U in V of WU times the absolute value of H hat U. So the argument that I just gave you gives you a lower bound. This is certainly, this quantity, you certainly have to pay this. Because if this is plus 0.1, you need to bring in 0.1 mass. If this is minus 0.1, minus 0.1 mass needs to go out. Okay, so this is certainly a lower bound. But again, by doing it by induction, you can prove that it's also an upper bound. You get a plan to actually do that. Okay, you just do the things bottom up. Okay, so this is the Wasserstein distance in this thing. And you see the thing that we don't like is that it's not as simple as before. It's not just a weighted L1 norm. It depends, it has this difficult operation that you're summing things in a subtree. So this is where the idea of a general convex set and expanded state space is going to be helpful. Instead of just doing mirror descent on the leaf, we're going to define variables for every vertex in the tree. So we're going to do a descent algorithm on every vertex in the tree, and at the end we only care about the leaf, but the internal vertices are helpful to track the movement. I'm not saying this is the only way to do it, but this is the cleanest way. Okay, so let me write now for you the state space case that we're going to use in this case. So the state space that we're going to use is the following. So basically, we're just going to have a variable x for every node u, and we would like to say that xu is equal to the sum of the xv for v, the child of u. Okay? So k, let me write this. K is going to be all the x in R plus v, such that you have the following. X at the root is 1. Okay, so the total mass in the system is 1. At the root it's 1. And for any u in v except for the leaf, what you want to have is xu is equal to the sum over all the v such that the parent of v is u. Okay, so I use this notation to say the parent of v. Okay, so the parent of vertex v is u of the xv. Okay, so this is the convex set that we're going to work with. Now recall that all the inequalities that we write, or all the equalities that we write, they induce movement through the Lagrangian. So we will have to deal with that. And it will make our life much simpler if instead of having a two-sided inequality like this, we have only one side. And the other side of the inequality is going to be enforced by the dynamics. So instead of writing equal, I'm only going to write that I want this. I want the mass to not diminish. I want to say that the sum of the children, they should contain at least all the mass of xu. And of course, the dynamics are going to enforce that they never contains more. I mean, you know, in this problem, if I could somehow get to 0 mass, I'm in great shape because I never get any cost. Okay, so we always want to reduce mass. So it's only necessary to enforce that you cannot reduce it below what the parent has. Okay, so you only need one side of the inequality. And an exercise, the second exercise for this lecture, is going to be show that for the dynamics, we write below. In fact, xu at any time t is equal to the sum of the v such that pv is equal to u of xvt. Okay, so right now you cannot do the exercise. I didn't tell you the dynamics yet, but this is what I asked you to do. Okay. So we're going to write dynamics, and I'm not going to show it, but it's not too difficult. I mean, it forces you to really understand what I'm going to write. Okay, so we only have one side, and this will make our life easier for everything. Okay, so what is a normal cone in this case? So what is a normal cone at x? Okay, so the normal cone, it has several terms. It has terms for the non-negative variables, and let me just check one thing. Yeah, okay. So it has a Lagrangian term for the non-negative constraint, which I'm going to denote by psi. It has a term for the root, and it has a term for, you know, each of those inequalities. So the normal cone, it looks like this. It looks like lambda is of the form minus the sum over all u in v of psi u eu. Okay, so these are the Lagrangian term corresponding to this. Then you have a mu at the root plus mu root times e root. And then you have the term corresponding to this, which I will write as follows, plus the sum over all u in v minus the leaves. And I'm going to write it as lambda u hat times eu minus the sum over all the v such that pv is equal to u, ev. Okay, so again, what is this vector? This vector is just, this inequality is just x inner product with this, with eu minus the sum of the ev is negative. Okay, so you just get this term. And the psi u is non-negative, lambda hat u is non-negative. This is the normal cone. And if they want to be strictly positive, then it has to be equal, and same thing for the psi u. And just as before, let's try to interpret what this is doing. So, where do I want to do it? Let me not do it in a little corner. Let's do it here. So, intuition. Intuition on the Lagrangian terms. So of course, you know, what does minus psi u, so psi u, okay, so I'm at vertex u, and I have all of those guys, all of those child v. So psi u, right, remember I get in the dynamics x dot of t, the time derivative of t, I get minus the Hessian inverse times c plus lambda. Okay, so I have a minus minus. Okay, so minus minus, so psi u comes as a plus. So psi u plus psi u, this is just a force that push so that I never go below 0. So force that push up so that xu is non-negative. Okay, that's what the Lagrangian term for this is doing. Okay, it's just pushing up. Now, what does lambda hat u does? So lambda hat u, you see it has a sign plus over there. So in this formula, it's going to have a sign minus. So lambda hat u, this push down at u and up at any v such that PV is equal to u. So lambda hat u, it's a force that push down here and push up here. Yeah?
Does it say in the square above?
Oh, the square is just to remind you the dynamics. Just the time derivative of x is minus the Hessian inverse applied to c plus lambda. Just the general mirror distance dynamics. All I wanted to bring your attention to is this minus sign. So really, you should think about minus lambda. Minus lambda is a force. Okay? So minus lambda is a force, so this minus psi u becomes a plus psi u. Okay, so plus psi u, this is a force that, you know, push up so that you never go below 0. And lambda hat u, you see it has a plus sign here, so in fact it has a minus sign with the minus lambda. It pushed down at u and up at any child. So the intuition, what this is doing, is that it's transferring mass. So it's saying this guy is going down and all of those guys are going up. And the reason is going to be this. So I have the leaves here, and I have something here, something there. And let's say, again, let's look at our example. Let's look again at our example where we just have a cost at location 1. Then in the dynamics, what's going to happen, I still haven't written down the dynamics, but what's going to happen is that the dynamics will tell me, push down at location 1. Okay, this guy, it should go down because of the cost. Then there is going to be a Lagrangian term at the parent, which is going to say some of this downward trend is propagated to this guy. This subtree is also going down. Okay, this child is going down, and this subtree is going down. Maybe this is going down, by 0.5, and maybe this guy is going to go down by 0.1. Okay, so out of the 0.5 decrease here, there is a 0.4 of the decrease, which is among just redistributed here, and then 0.1, which is going to be redistributed higher up. Okay, so that's what the Lagrangian term is doing, is that this guy is going down. Some of him going down means this guy is going down also, but its siblings are going up. Okay, so there is some transfer of mass going like this. But then it's also true at higher level. So at any level, some of the mass which is going downstairs is going to make this guy go down. And there is some mass transferred like this. And this is true everywhere. So there is mass transfer like this, like that. So this is what those Lagrangian terms are doing. They are doing all the work for us. Okay, so the mirror descent dynamics is just going to say, I want this. I'm not happy to be here. This guy is suffering some cost. Let's go down. Let's reduce the mass there. And the Lagrangian are doing the redistribution for us. Of course, they are doing the redistribution being helped by the Hessian of the mirror map. So that we will need to explain.
Sebastian.
Yeah.
So this lambda hat, they are like you said, it's made for any lambda hat, or?
Yes. This is for any lambda hat, and then it can be strictly positive if and only if this inequality is tight.
Are we going to choose some special values of these guys?
Very good. So this is the point of, again, mirror descent not being a differential equation, but being a differential inclusion. Okay? So the existence theorem is choosing for us. Then you might complain that this is not an algorithm, and okay, we can talk about that forever, but yeah, let's not do that. Okay. All right, so now let me write the mirror map that we're going to use, the dynamics, and conclude the proof. So we're going to use a multiscale entropic regularization. Okay, so let's call this 3 maybe. So far this was just set up for things on a tree, right? We didn't really write the mirror descent algorithm yet. So now we write the mirror descent algorithm, multiscale entropic regularization. And this pen is dying also. Let's see if this is working. Yeah, not much better. Okay. So the formula, and I'm not going to spend too much time on trying to justify it. We'll just do the proof, and then you can think about it. It's going to be the sum over all vertices of, so I will have just a 1 over eta just as before to normalize thing, and then I will have WU, XU plus delta U log XU plus delta U. And delta, again, I'm going to be smart, I'm going to choose it in K such that, A delta equals B, where K is, I write it out of the form non-negative and AX equals B. So what this is saying is just delta, it's 1 at the root, then, it's 1 over the size of the children, of the child, and over here it's just 1 over n. 1 over n, 1 over n. Okay? So again, phi is log 1 over delta over eta Lipschitz. This is the same calculation as before. Okay? This is just the same as before. And 1 over delta is 1 over n, so this is really log n over eta Lipschitz. Okay? So I'm going to choose eta again to be log n. Okay, I choose eta to be log n, and I already get now st is bounded by st star plus mt star. Okay, I have set up everything so that this is true. So now I need to talk about the movement. And to talk about the movement, I'm going to write what is the dynamics. So you see, it's going to be exactly the same as before. When I take the Hessian of this, I just get WU over XU plus delta. Okay? So when I write the Hessian inverse, I will just get XU plus delta U. So here is the dynamics. And the dynamics writes very nicely if you use the Hadamard product notation. So Hadamard product just means entry-wise product. Okay, so just entry-wise between two vectors. So then the formula becomes that the Hadamard product between W and the time derivative of x of t. Let me just rescale things by W, it just makes nicer. This is equal to minus x plus delta Hadamard product with c plus lambda. Okay, this is exactly the formula that you get when you write down the Hessian inverse. You know the Hessian inverse is going to be a diagonal with xu plus delta u over wu, and you hit it with c plus delta, so you get this. And lambda, again, lambda is like that. Okay, so now the only thing that I need to worry about is the norm of the time derivative of xt. What is this? Okay. And now you see that the situation is more complicated. Because those lambdas, they make me go up, they make me go down, you know, they have all sorts of signs everywhere. Okay, so the analysis is more complicated. And here, the trick is going to look only at things which are going up. Okay, so things are only going up for one reason. They are only going up because of the lambda hat u. Okay, so what we're going to look at here is the positive part of the movement. Okay, so we're going to look at mt plus, time derivative of mt plus. And where is the positive movement coming from? So where is the positive movement coming from? Well, it's only coming from, you remember this picture, this is going down and those guys are going up. It's only coming from the lambda hat u. These are the guys that induce positive movement. Okay, the psi u, they don't really introduce movement, they just stop you. They just stop you at zero. So the only thing that introduces movement is lambda hat u. Okay? So, and the way it introduces positive movement is by pushing mass down the tree. Okay, where is the positive movement coming from? It's mass going down the tree. And now here is an idea, a really beautiful idea due to Michael Cohen, absolutely amazing, which is to look at what is called the weighted depth potential. So weighted depth potential. So this is a new potential. In addition, so you know, in our proof right now, in the proof of this statement, we already had a potential, which was the Bregman divergence. Now we're going to have a new potential, an auxiliary potential, and it's going to be defined like this. Psi of x is going to be the sum over all vertices u of v of the depth, so this is the depth of u, times weighted mass. Okay, which we're going to write as the inner product of d with the Hadamard product of w and x. Okay, so d is a vector which contains the depth, and this is what we write. Okay, and I will go over, I started 5 minutes late, so I have until 4:20. So I just want to finish this, and then we will be done. So this is going to be the thing that tracks, so you see, this is not really changing, because the time derivative of this, at any level, the mass remains constant. So this is an invariant, in fact. It's not really a potential, it's an invariant. It stays to be zero all the time. But it's going to allow us to track how is the mass going down the tree related to the initial cost at the leaves. So let's see how this works. So let's take the time derivative of psi of x of t. Okay, so this is d, the inner product of d, with w times the time derivative of x of t, which I have nicely written. It's just this over there. So this is equal to minus d inner product with x plus delta, Adama product with c plus lambda. Okay, so we find there will be two terms. So the x plus delta times c, this is at depth capital D, the final depth. So this is equal to minus capital D times x plus delta inner product with c. And then there is another term which is minus d times x plus delta inner product with lambda. I mean, Adama product with lambda. This is bounded by twice the service cost. Right? This is the lemma we had before. X plus delta times c is bounded by twice the service cost. So x times c is x times c, but delta times c is bounded by x times c plus some time derivative of a potential. So what we see is this potential, we have minus the depth times the service cost. And what I'm going to show to you is now this term is nothing but the movement cost, the positive movement. So what we'll get is that the positive movement is equal to d, capital D times the service cost. Okay, so let me say that. So we're almost done. So we show now that d times x plus delta inner product with lambda is in fact the positive movement. The positive movement delta t of mt plus. And what does this mean? This will imply that the positive movement is in fact equal to the depth, so 2 times the depth times the service cost plus or minus some potential times the time derivative of psi of x of t. Which means now that the movement is going to be the depth times the service cost. Okay, so this will imply that mt plus is going to be bounded by 2d st plus a constant. And as always, I always forget the eta, right? I mean, things are renormalized with an eta. So there will be eta, which is log n, so I get log n times the depth. Okay. So the only thing that I need to show is this calculation. And how much time do I have? Okay, 3 minutes. Let's do that. So this is the final calculation, and this is really the beautiful calculation where I'm going to use the fact that I have the depth here. Okay. So, and I'm probably going to mess it up, but let's see. So, depth times x plus delta inner product with lambda. So what is this? This is a sum over u of, yeah, that's exactly not what I want to do. So let's look at what is x plus delta Adama product with lambda. Okay. So what do I get? I get a sum over u in v minus L, and I get those lambda hat u, And they are against what? So I get xu plus delta u minus times EU minus the sum over V such that PV is equal to U of xV plus delta V times EV. Okay, now we're set up for success. This is going to work. So this is what is lambda. And I don't need to worry about the xi-u because the xi-u, they don't make things move. Okay, so I just forget about it. This is the only thing that matters. And now I inner product, so this is a vector, and I inner product this with d. D times x plus delta, Hadamard product with lambda. So what is this? So when I inner product this, I'm going to get the sum over u. I will have lambda hat u. And then I get du times xu plus delta u minus the sum over v, such that pv is equal to u, of dv xv plus delta v. But what is the depth? U is here, v is there. So du, what is dv? dv is du plus 1. Okay, so dv is du plus 1. And what is the sum of xv plus delta v? It's xu plus delta u. Right? Just because by conservation of mass and by the fact that delta is in k. So in fact, this is du plus 1 times xu plus delta u. So in fact, this is equal to the sum over u of lambda hat u xu plus delta u with a minus sign. Which is exactly the movement, the positive movement. The positive movement is exactly this. Okay, so this is exactly the time derivative of m plus. Yeah, so this is some magic. And it simplified lots of ugly and long calculations into this very nice thing.
So we don't need to worry about the size because they don't make the
Yeah, the size, they just stop you. So in fact, if psi is acting, then it means that the corresponding x is 0.
So I just don't need to worry about them in the calculation.
Yeah, you don't need to worry about them in the calculation.
If I write them down, they just cancel out?
If you write them out, yeah, because it will be inner product with x, and then, you know, x itself, if this is non-zero, x is 0. Yeah.
Last sum, are you summing the leaves? Or
Say again?
are you summing the leaves in the last term?
Okay, good question. Good question. Am I summing the leaves in the last step? Let me just think. Am I summing the leaf in the last step? That is a very good question. So I want this. Am I summing the leaf in the last step? No, I'm not summing the leaf in the last step. And this is correct. So you see, in here, the only part that matters, the part that we're looking at, is this part. And in this part, the EU is over U, which is in V minus the leaves. And the only movement that we're monitoring is this inner product with x plus delta. Yeah, thanks.
So just to make sure, so
Yeah.
you're not summing the leaves.
I'm not summing the leaves because the only movement that I care about is this one. And in fact, now that I write this, I guess I am looking at the negative movement. Because this is the movement. Yeah, I'm looking at the negative movement, sorry. So this is a negative movement, right? This is a movement which is induced by those Lagrangian term and going back up the tree. In fact, I am looking at the negative movement. Yeah. And you see, at the end of the day, I get log n times the depth and a one competitive service cost. Okay, that's it for MTS.